Continual graph learning, CGL, is a challenging task that aims to extend static graph neural networks, GNNs, to dynamic taskflow scenarios. Existing experience replay, methods, inspired by the complementary learning systems theory, have achieved state-of-the-art performance in CGL. However, these methods focus on identifying samples by feature significance or topological relevance, limiting their utilization of comprehensive graph data. To bridge this gap, the proposed feature-topology fusion-based experience replay (FTF-ER) method integrates information from both feature and topological levels to mitigate catastrophic forgetting in CGL. FTF-ER employs two theoretically grounded approaches to calculate node importance scores: gradient norm score (GRAND) for feature-level importance and Hodge Potential Score (HPS) for topological level importance. HPS uses Hodge decomposition on graphs, HDG, to calculate the topological importance of nodes, providing more accurate global topological information compared to neighbor sampling. The FTF-ER workflow involves selecting nodes from each class based on importance scores to create induced subgraphs for the buffer. This enables the model to maintain classification performance across tasks. Experimental results on 4 mainstream graph datasets demonstrate that FTF-ER achieves state-of-the-art performance in the class-incremental learning setting, with significant improvements in accuracy and F1 score. The proposed method addresses the limitations of existing methods, which focus on either feature or topological information and neglect global topological information. FTF-ER provides a novel approach to continual graph learning, leveraging both feature and topological information to mitigate catastrophic forgetting. By combining Hodge decomposition and node importance scores, FTF-ER efficiently captures comprehensive global topological information in the node sampling phase, eliminating the need for additional nodes during subgraph creation. The authors propose a novel feature topology fusion-based experience replay (FTF-ER) method for continual graph learning, CGL, aiming to learn a model that can continually adapt to new tasks without forgetting previous ones. FTF-ER leverages both local and global topological information to select the most valuable nodes from the complete training dataset for efficient graph learning. The authors introduce a new Hodge Potential Score, HPS, to measure the global topological importance of nodes, which can achieve more accurate global topological information compared to other topology-based methods. By applying HPS, the storage overhead during model execution is significantly reduced. A fusion strategy is also presented that combines HPS with GRAND, a local node importance scoring function, to leverage comprehensive graph data. Experimental results on 4 public datasets show that the proposed FTF-ER method outperforms current state-of-the-art methods in the CGL field and performs similarly to the joint training method. This indicates that the FTF sampling strategy effectively selects the most valuable nodes from the complete training dataset. Further analysis reveals that the FTF-ER method significantly outperforms other CGL methods under the class IL setting, with improvements in both average accuracy and average forgetting. The proposed method addresses the catastrophic forgetting issue in CGL by fusing feature-level and topological-level information. The method leverages Hodge decomposition on graphs to calculate the topological importance of nodes without additional storage space, obtaining more accurate global topological information compared to local neighbor sampling. Experimental results demonstrate that FTF-ER outperforms state-of-the-art methods, including fine-tune, EWC, LWF, MOS, GEM, ERGNN, TWP, and SSM. Ablation studies show the effectiveness of the proposed node sampling method, which integrates feature-level and topological-level information. The results also indicate that the fusion of feature-level information and topological-level information surpasses the approach of using only one of these types of information. In terms of computational overhead, FTF-ER has nearly the same buffer memory overhead as ERGNN and significantly lower than the SSM and GEM methods. The method also achieves the best overall training time among all ERBASED-CGL methods, mainly attributed to treating topological importance calculation as a preprocessing step. The feature-topology fusion-based experience replay (FTF-ER) method is introduced as a novel approach to continual graph learning, leveraging Hodge decomposition to better understand graph structure and improve the learning process. This approach combines node features and topological information using a Hodge decomposition-based feature fusion strategy, helping to identify and preserve essential information from previous tasks and reduce catastrophic forgetting. An experience replay mechanism stores and samples experiences from past tasks to further enhance learning. The Hodge decomposition theorem on graphs decomposes a graph signal into three orthogonal components: gradient, curl, and harmonic. Mathematical operators, such as the gradient operator, negative divergence operator, and graph Laplacian operator, are used to compute topological importance of nodes in a graph. The graph Laplacian operator corresponds to the usual graph Laplacian operator, a fundamental concept in graph theory. Experimental results demonstrate the effectiveness of node representations learned by the FTF-ER method. A qualitative analysis on the Amazon Computers dataset shows that FTF-ER exhibits a clearer separation of nodes from distinct communities compared to alternative methods. Sensitivity analysis of the hyperparameter beta demonstrates its different effects on various datasets, with the peak consistently occurring at the middle position on all datasets, confirming the effectiveness of feature topology fusion sampling. The FTF-ER method is evaluated on various benchmark tasks, demonstrating its effectiveness in overcoming catastrophic forgetting and improving performance on subsequent tasks. The use of Hodge decomposition in experience replay mechanisms provides a robust framework for learning and preserving knowledge across tasks, making it an important contribution to the field of continual graph learning.